Okay, so binary search tree. A binary search tree, it is also a binary tree, and it may be empty, or if it is not empty, then it satisfies the following properties. That is, every element it has a key, and no two elements have the same key. That is, no duplicates is allowed. Every element has a key, but no two elements have the same key. That is the first condition. The second condition is the keys in the left subtree are smaller than the key in the root. The keys in the left subtree are smaller than the key in the root, and the keys in the right subtree are larger than the key in the root. The key in the left subtree, it should be smaller than the root. The key in the right subtree, it should be larger than the key in the root. Then the left and the right subtrees are also binary search trees. So the left and the right subtree, that also should be a binary search tree. So a binary search tree, that is also a binary tree with some extra properties. Uh, that is, it may be empty or it may not be empty. If it is not empty, then it should satisfy the following properties. That is, every element it has a key, and no two elements have the same key. Then the key in the left subtree, it should be smaller than the key in the root, and the keys in the right subtree, it should be larger than the key in the root. Also, the left and the right subtrees are also binary search trees. So this is a binary search tree. The root is 7. Its left child is 2. Left child is 2. That is less than 7. Its right child is 8. So 8 is greater than 7. So its right child is greater than root, and left child is less than root. When you look at this subtree 2, 1, 4, when you look at this subtree, you can see that the root is 2, its left child is 1, that is 1 is less than 2. Its right child is 4, that is 4 is greater than 2. When you look at this subtree, that is 4, 3, and 5. 4 is the root, 3 is the left child, and 5 is the right child. So 3 is less than 4. So its left child is less than the root, and its right child is 5. 5 is greater than 4. Then when you look at this subtree 8, 9, it has no left child. It has no left child, but it has a right child. Its right child is 9. So 9 is greater than 8. So this is a binary search tree because it satisfies the condition that the left child is less than the root, and the right child is greater than the root. When you look at the complete tree, when you look at this tree as a complete, uh, uh, you can see that all the values in the left side of 7, that is less than 7, that is 2, 1, 4, 3, 5, all these are less than 7. When you look at these right subtrees, all the values are greater than 7, that is 8, 9, all these are greater than 7. So in a binary search tree, the left child or the left subtrees will contain value less than the root, and the right subtrees or the right child will contain value greater than the root. Let us look how to construct a binary search tree. So let us insert the values 7, 2, 1, 4, 3, 8, 5, and 9. And first I will insert 7. So I have inserted 7. 7 is the root. Now the next element coming is 2. So I will compare 2 and 7. When I compare 2 and 7, I find that 2 is less than 7. 2 is less than 7. So I will give it to the left side of 7. Next element coming is 1. So 1 is, I will compare 1 with 7. 1 is less than 7. So we will go to the left side. Again, I will compare 1 and 2. 1 is less than 2. So I will insert 1 as the left child of 2. Next element coming is, next key is 4. So to insert 4, I will compare 4 and 7. Since 4 is less than 7, we will come to the left side. And I will compare 2 and 4. But 4 is greater, so I will insert 4 to the right side of 2. The next key is 3. So I will compare 3 and 7. So 3 and 7 3 is lesser, so I will come to this left side. Again, I will compare 2 and 3. So 3 is greater, so I will come to this right side. Now I will compare 3 and 4. 3 is lesser, so I will insert 3 to the left side of 4. The next key is 8. So I will compare 7 and 8. Since 8 is greater, I will insert 8 to the right side of 7. The next key is 5. So I will compare 5 and 7. So 5 is lesser. So I will go to the left side. Again, I will compare 2 and 5. So 5 is greater. So I will go to the right side. Now I will compare 4 and 5. So uh, since 5 is greater than 4, I will insert 5 to the right side. As I will insert 5 as a right child. Next key is 9. So I will compare 9 and 7. Comparing 9 and 7, 9 is greater, so I will go to the right side. Comparing 8 and 9, I find that 9 is greater. So I will insert 9 to the right side of 8. So in this way, we can construct a binary search tree. Questions may be asked like this. You will be given a number of keys and you will be asked to construct a binary search tree using the following keys. So if such a question is asked, you have to do in this way. You have to draw a binary search tree like this. You have to insert all the keys one by one. Okay. Next is searching in a binary search tree. Searching for data in a binary search tree, it is faster than in arrays or in linked list. So the applications where frequent searching operations are to be performed, this data structure is used. To search for an item, we will start from the root node. Then if the item is less than the root node, we will proceed to the left child. If the item to be searched is less than the root node, then it is sure we have to go to the left side. So we have to proceed to the left child. If the item to be searched is greater than the root node, then proceed to the right child and continue the steps 2 and 3 till the item is found or we reach to a dead end. We will repeat these steps until we find the item or until we reach the leaf node. So in such a way we can do searching. So this is the algorithm for performing search operation in a binary search tree. So PTR is a pointer to the root node. PTR equal to root. Then I am using another variable flag, which is initialized to false, flag equal to false. Then while PTR is not equal to null, while root is not null and flag equal to false, do. That is, repeat these steps. Here 3 cases are written. The first case is if item is less than ptr.data. That is, the item to be searched is less than ptr.data, then we have to go to the left child. Our item is having a lesser value, so you have to search in the left side or the left subtree. So we will update ptr as ptr equal to ptr.left child. Then as the next case, we will check whether the ptr.data is equal to item. That is, whether the data at the root node is equal to item. In such a case, flag equal to true. That is, we will set the flag. The next case is if item is greater than ptr.data. If the item to be searched is greater than ptr.data, then we have to search in the right subtree. So we will update ptr as ptr equal to ptr.right child. So this is a while loop. So this will continue until this condition become false. Then if flag equal to true, once exiting from this loop, we will check if the flag is true. If flag is true, then it means that we have found out the item. That is, the item is found at the node. Otherwise, we will print the item does not exist and the search is unsuccessful. Okay, so for searching for an item in a binary search tree, we will check the item with the data in the nodes starting from the root. So first we will compare with the root node and we will check whether the item is less than or greater than or equal to the value at the root node. If it is equal to the value at the root node, we will set the flag, that is we have found out the item. Otherwise, we will update our node, that is initially PTR is set to root. Now we will update PTR to ptr.leftChild. If our item is less than the value at the root node, we will update PTR as ptr.leftChild. Otherwise, if the item is greater than ptr.data, then we will update our PTR as ptr.rightChild. So these steps will repeat and we will get the final answer whether the item is found or not. For example, suppose let us search for 6. So the PTR, the root node or the PTR node is node 5. So first we will compare 5 and 6. Since 6 is greater than 5, we will update our PTR. Now my PTR will become the right child of our new PTR is updated as PTR will be the right child of node 5, that is the right child of node 5 here is 7. So I will now compare 7 and 6 and I find that our item, that is 6, is less than 7. So we will go to its left child. Now I will update my PTR. Now PTR is 6, so I will compare 6 and 6. Now 6 and 6 is equal, so we have found out the item. Item is found. So this is the search operation. The next operation is insertion. Insertion operation in binary search tree. Before inserting, we have to find the appropriate place for insertion. Before inserting a node into a binary search tree, we have to find its appropriate position. So here first we will write a while loop for searching and finding the exact position of insertion. For that we will write one while loop, and after that we will create a new node and we will insert that node. So the first steps, that is this while loop, this is almost similar to the search operation. This algorithm, the initial steps of this algorithm is almost the same as that of the search operation, because first we have to find the exact position for insertion. Then only we can create a node and insert that node. So first we will take PTR equal to root node and we will initialize flag to false. Then while PTR is not equal to null and flag equal to false, we will write 3 different cases. The case 1 is if item is less than ptr.data, then I am assigning PTR to PTR1. So PTR1 equal to PTR, then PTR is updated as PTR.leftChild. That is the item. If the item to be inserted is less than PTR.data. PTR.data means in initial case it is a root node's data. If the item is less than the root node's data, then we have to insert this node as the left child. So we have to go to the left subtree. For that, I am updating my PTR as PTR equal to PTR.leftChild. The next case is if the item is greater than PTR.data, then PTR1 equal to PTR, then PTR is updated as PTR.rightChild. That is, we have to go to the right side of the tray. Then the next case is if the PTR.data is equal to item. If PTR.data is equal to item, then we will set the flag, that is flag equal to true, and we will print item already exists. So these initial steps will find the position for insertion. So once that is going to either to the left side or to the right side, for finding that we write this while loop. Then after that, once quitting from this execution, from this loop, we will come to step 16, that is if PTR equal to null, then that is After going through this while loop, we will reach a leaf node. So we will check if PTR equal to null, then we will create a new node. New equal to get node of node. We will create a new node and we will assign the item to its data portion, that is new dot data equal to item. Then new dot left child equal to null, new dot right child equal to null. The left and the right addresses will be set to null because the new node created, it will not have a left subtree or a right subtree. So that is initialized to null. And if ptr1 dot data is less than item, then ptr1 dot right child equal to new. If ptr1 dot data is less than item, that is the item we are going to insert, if it is greater than the current node's data, the current node ptr1, the current node's data portion is less than item, or our item is greater than ptr1 dot data, then we will update our, or we will insert our node as a right child. So ptr1 dot right child equal to new. We will insert our item as the right child. If our item is greater than ptr1 dot data, we will insert our item as the right child. In the else case, we will insert our item as the left child. So ptr1 dot left child equal to new. We will insert as the left child. So this is a sample input. So we have a binary search tree 42713. These are the nodes in this binary search tree. And suppose we are going to insert 6. So first we will compare 6 and 4. Since 6 is greater than 4, we will go to the right side. We will update PTR, that is, we will go to this right side. So we will compare 6 and 7. So when comparing with the 6 and 7, we find that 6 is lesser than 7. So we will insert 6 as the left child of 7. We will insert 6 as the left child of 7. So this is the status of this binary search tree after inserting 6. Let's look at another example. Suppose we are going to insert 17 to this binary search tree. The root node is 20. So 20 will be compared with the 17. So since 17 is lesser, we will go to the left side. We will update our PTR and we will go to this left side. So the next node is 15. So 15 will be compared with the 17. Since 17 is greater, we will go to the right side. That is, we will go to this side. Now PTR is updated as 18. So 18 will be compared with the 17. So comparing 18 and 17, we find that 17 is lesser. So we will go to this left side. So we will update our PTR to 16. Now we will compare 16 and 17. So when comparing 16 and 17, we find that 17 is greater. So we have to insert 17 as the right child. So 17 is inserted to the right side of 16. So in this way, insertion can be done. So for insertion, first this algorithm, either to the, first we should go to the either to the left subtree or the right subtree. This portion is needed, then we will create a new node and we will insert it to either the right side. That is, we will insert as either the right child or the left child of the current node.